In this video, I am going to talk about epsilon delta definition of limit. Typically, when we find limit for a function at a particular point, what we do, we try to manipulate the function in such a way so that we can see the behavior of the function as x approaches the particular value of interest a, or we try to graph it and see how does the graph looks like. However, there is a formal definition of limit that exists, and this is the definition from a mathematician's perspective, and this is how it kind of goes. Let's consider a function f of x, okay? And we are interested in finding the limit of this function as x approaches a. And let's call this limit L. Let's, for the sake of argument, assume that the limit does exist. And A is a point that is contained in an open interval. Open interval. Now, for the sake of argument and simplicity, open interval for you guys is nothing but just an interval that does not include the boundary. So, for instance, something like 1 to 2 is an open interval because it does not include the boundary point 1 or 2. On the other hand, a closed interval would be something like 1 comma 2. This includes the boundary points. So let's consider this open interval C to D, okay? And A is an element of this, okay? This is a symbol we use in math to indicate that something belongs to something else or element of. By the way, let's not confuse with this and this. This is epsilon, and this kind of looks like this too. Maybe it's the same thing, but anyway, so we say the limit of the function f of x as x approaches a exists, and it happens to be L if these conditions are satisfied. If for every epsilon greater than 0. It could be as big as you want or as small as you want, okay? Typically, when we say epsilon greater than 0, we mean that it's a smaller value. So, for every epsilon greater than 0, we can always find, okay? We can find a delta greater than 0 such that, so remember, for every epsilon greater than 0, we can find, or we can say there exists a delta greater than 0 such that whenever 0 is less than absolute value of x minus a is less than delta, we will have f of x minus L, the limit, presumed limit, is less than epsilon. Now, if you're taking calculus for the first time and you're seeing this epsilon delta definition, this may be a little bit difficult to grasp. It may be a little confusing and whatnot. So please don't give up or don't be frustrated. I don't expect you to get an in-depth understanding of this definition, but if you do, that's wonderful. I'm happy for you. It's a definition. It takes a little bit of time to digest, okay? A little bit of time to get a real feel for it. Just to give you a sort of graphical view of it, what it's saying is this, by the way. If you have this number line where, let's say, your point A belongs here, if you restrict your values of x between some delta, positive delta from A and some negative delta from A, that means you're keeping it between, keeping it in a window, okay? So if your x approaches A and the difference between the value of x and A, absolute value of it is less than delta, then what's going to happen for those values, the difference between f of x and the actual limiting value would be less than epsilon. So by controlling the epsilon, we can control the delta too. So that means I can make my epsilon as small as we want, and we will always be able to find a neighborhood or window around A there's gonna be ensuring that the difference between f of x and the limit is gonna be less than epsilon. So it's kind of like the squeeze theorem. You're squeezing the value of the function f and the fixed value L. Their differences, you want to make them as small as you want, okay? And you can make it arbitrarily small. By that, what I mean is that you can make it as small as you wish. That means the difference between the function value and the limiting value, you can make it as small as you prefer. There is no limit to it. Doesn't matter how small you make it, you'll always be able to find a certain set of values that are around a, certain set of values of x that are around a, which values are gonna ensure that this difference between f of x and L is less than the epsilon value. That means whatever value that you decided. So, moral of the story is that you can bring the function arbitrarily close to L, the limiting value. It doesn't matter how close you want, as close as you wish. That means in the limiting case, that this difference is technically going to be what? Approaching 0. And what happens is that regardless of the value of this epsilon, we can always find the corresponding delta, which will ensure us that if my x is in between this positive delta and negative delta, the difference of f of x and L, absolute value of it, is going to be less than epsilon. If this doesn't make sense, watch a couple of other videos online on epsilon delta definition. Maybe they will give you a different perspective or even a better way of explaining this concept. This is not an easy concept. It's a bit harder concept. So I would recommend watching a few videos, hearing it from different folks, and get a different perspective or different ways of understanding. Okay, I hope that this discussion was helpful. Thank you very much.